Hello everyone. This is an extension video of the infrared communication series. So in this video, I am going to talk about the communication protocol I am using to transmit data between the transmitter and the receiver. So as in the previous video I have discussed, this is the transmitter circuit, this is the transmitter part, this is the transmitter LED, and this is the receiver part with the receiver module and the Arduino Uno, and we are giving a command to the transmitter from the serial monitor, and we are getting the reply on the relay, the status on the relay. Whatever we have written on the software, that particular LED has to switch on. So in the last video I had only one LED and I successfully switched on and switched off this LED. This can be extended. In another video I will show how to extend with a complete relay board. But in this video I am going to discuss how the software protocol is working, because infrared communication is a single communication. It is not a duplex communication. It is a simplex communication. So whatever I am sending, I don't have any feedback what it is receiving, the data is tampered or what's happening with the data, where to start the communication, where to end the communication, how to handle the error. We have many limitations. So in this video I am going to discuss how my protocol is designed for the communication. I am using a basic protocol. It is my own protocol and I will discuss my own protocol. So I am going to explain the theory. So in the theory we can see when a data transmission is going to occur, a data 1 means a high pulse and a 0. A 1 and a 0 means a data 1. Okay, so 1 and 0 together makes a data 1. And how it is interpreted in the receiver module, when the 1 is received, there will be an interrupt. On the software there will be a software interrupt. Due to the software interrupt there will be one shift of the data, and since there will be a shift on the data, after it returns from the interrupt, on the software by default there will be another shift. So when there is a pulse detected, there will be two shifts of data. As you can see, there will be two shifts of data. Two physical shift registers will activate. Okay, so two physical shift registers will activate. I will show on the software how it is behaving. Similarly, when a 0 is received, means no signal is received, there is no light from the transmitter, what the receiver will do? The receiver will be silent. The receiver software by default will have a delay. It will first shift with a 0-0 pattern. It will first do a shift, and then again it will have a delay, then it will make another shift. So technically there will be two shifts here also. So why here I am writing 0-0? Because I have to maintain the time. See, there is a time, for this time it is 1-0. So when no signal it is 0-0. But here there are two shifts. Why? Because interrupt is called, the software will call a shift, and the software by default will call another shift. So here there is two shift, but here there is, since it is a 0, the software will call only one shift, but we have to call two shifts in order to make the receiver compatible with the transmission. Okay, so for that we have to make it like this. We have to have two shifts. So this is how the software is designed. You can see, so this is how the protocol behaves. So again I would like to say, since the interrupt is having a 1, since there is a 1 received, means the transmitter LED has glown, receiver has received it, there is a 1 detected, the interrupt will have a shift and the software will have a shift. But when there is no signal, we need to maintain the time, and we need to maintain two shifts. One shift for this 1 and one shift for this 0. So two shifts we need to maintain. That's why we are using it like that. We are sending two zeros, like 2-0-0-0-0. Okay, so I am going to show it in the software now. So as you can see here, when 1 is transmitted, you can see here I am sending 1. So what the transmitter is telling, transmit out on, transmit out off. Okay, means give a pulse and then switch off the pulse. Wait for 1 second. This is a 1. Okay, so let us see on the circuit, same thing. Let us see on the theory, the same thing. On the theory, the same thing is high and a low. See, on the software how it is. On the software also it is, see, on one high and a low. This is how the LED. This is the command to switch on the LED, to send a 1. Okay, same the thing is implemented here. Same thing, see, 1 and a 0. Okay, so now when I am sending 0, I am sending 4 zeros. So you can see it here. TX out, off, delay, off, delay. Okay, so you can see here 0 0 0 0. So like that. Yes, you can see the transmitter has sent off. Okay, like this. Now I am going to show the receiver part, how the receiver part behaves when a data is received. So as you can see, I have reserved pin number 2 of the Arduino Uno with an interrupt. Okay, so when I am getting a rising edge, means the pulse rising edge, when I am getting, it is going to call a routine blink. Okay, it is going to call a routine blink. So whenever the LED is on from the transmitter, the receiver detects it and it will give a blink. It will call the routine blink. So what's there in the routine blink? Let us see. So when the routine blink is called, there is a 16-bit data shift. You can see the 14th bit is shifted to 15th slot of the array. You can see the 13th slot is shifted to 14th slot. 12th slot is shifted to 13th slot. There is a shift register. The data shifting is there. So serially data is received on the transmitter. Serially data is received on the transmitter and the data is shifted. Whenever the interrupt is there, whenever there is a call from the transmitter that there is a high pulse, it will by default shift the data. You can see here it will by default shift the data. It will call the interrupt and on the interrupt routine it will shift the data. So as you can see here now, further after shifting the data, what the software will do, the software will upload it in 2 variables. This is the final variable, this is the final variable. Okay, so this is 16-bit variable, this is 8-bit variable. So the software will, whatever is recorded, it is long data. So 8-bit, it will be recorded in a 16-bit initial register, and on the final register it will again record, and you can see a difference between initial and final register. See here the 15th bit, 14th bit, 13th bit, all the bits are there on the main register, but on the final register you can see only the odd number bits are there, 15, 13, 11. Why it is like this? Because you can see on the software, see, if this is 15th bit and if this is 14th bit, this bit doesn't make sense. There is no physical importance of this bit. This bit is used for a padding. This is just a padding bit. So padding bit has no usefulness. That's why on the software final processing, when I am final processing the data, I am not using the padding bit. You can see 14 is the padding bit, it is omitted. You can see the main bit 13 is used. So like this you can see 11 is there. See 12th bit is the padding bit. It is not here. You can see after 13 directly 11 came. There is no 12. There is no padding bit. So like this this is the final register. This is the final register. Okay. So on the final register, whatever we are sending, see we will send, if we want to send 1, we have to send 1 and 1's complement. The transmitter will send, it will not directly send 1. It will, if it sends directly 1, then when it is sending 2, there will be a clash. There will be a clash. It will think that it is detecting 1. It will confirm 1 is received and it will give a confirmation. So to prevent this kind of error, we are using 1 and 1 complement to confirm 1. You can see 1 and 1 complement, it is comprised of 1. So here you can see how many bits, 4 bits here, 4 bits here and 4 bits here, 1 byte. Okay, so total 8 bits are here. So you can see here, this is the this variable contains the final processed received data. This variable contains the final processed received data. The above this variable will consist whatever is received, and this one will receive it will have the final processed data, because here it will have paddings, here it will not have any paddings. So this is the final real data. So the software will check this variable, and it will take the decision what to do and what not to do. So that I am going to explain now again. So when there is a 0 received, means there is no data received, there is a timeout. It is looking for a data, no data, delay. Then it will, by default it will shift. You can see by default it will call a shifting operation. It will call a shifting operation with a 0. The whatever data on the main register will be shifted, because within the time frame there is no data, but we have received a 1. So the reception is in progress. That's why immediately it will, by default it will wait for 1 second, and it will rotate the register, and it will shift it so that the next data can come. Okay. So you can see here another thing. So whenever it is rotating, the last value it will rotate it as a 0, because when nothing is received, there is no interrupt call. When nothing is received, there is no interrupt call. We have to assume that it is a 0. We cannot say there is no data. We can say this is a 0. Nothing is received is a 0. Okay. So it will directly show here a 0 is received. Okay. Physically there is no LED blink, but it will confirm there is a 0. Means I didn't receive any data. So once it is shifting, then it will finally update the main register. You can see on the interrupt also, you have seen same main register was there. So whatever it receives, it has to update the main register. So this is the main register, and this is the processed register. So processed register, as I have told before, it will remove all the paddings, and the main register will have all the paddings. Okay, so what is the padding? Again I will say what is the padding. When I am sending 1, I am sending 1 and 0. So 0 is the padding. Here 0 0 means only 0 is the real data, 0 is the padding. Okay, like that it is. So now as you can see, I am going to show you how the software decides now. So see, when there is a 0 0 0 0 means there is no data, then it will tell whatever the last data it has detected, it will display. You can see whatever last data it has received, it will display the last data. Whatever last data it has received, it will display. And other than that, when it receives a 1, you can see here 0 0 0 1 1 1 1 0 1 1 complement. If it receives 1 and 1 complement, it will tell 1 is detected. It will make the variable confirmation 1. Okay, similarly, when it receives a 2, it will receive 0 0 1 0, and the 2's complement is 1 1 0 1. It will confirm 2 is detected, and it will make the variable 2. Similarly, when it receives a 3, what will happen? It will receive 0 0 1 1. The complement is 1 1 0 0. It will detect 3 is detected, and it will show the variable count is 3. Like this up to 8, all the variables are here. So this is how the circuit works, and it will process, and finally it will show whenever there is no data, the register is 0 0 0 0, all values are 0. It will show, it will come to know there is no transmission now, and then it will show the last received data. So you can see, and then it will do the required, it will give the required output. It will switch on the required LED. So when it is detected that it is having the last data, it will check whatever is 5, 4, whatever it is, it will do that action. So this is how my software is working. So this video was a little long video, but this is the way how the protocol behaves, how I have designed my own protocol. So this is how I have designed my own infrared protocol, and the protocol is working fine. Data is communicating and it is a successful protocol. It is my own basic protocol for infrared communication. Thanks a lot. Thanks for watching.